Okay, before we talk about horizontal asymptotes, I'm just going to throw a little bit of calculus at you, and it's cool if this kind of like feels weird. This notation it means limit. You'll be totally comfortable with it once you learn it more. But it's an idea that you could totally understand right now. All right, so the limit as x approaches infinity as of 1 over x is equal to 0. So like, what the heck does that mean? Well, if we look at a graph of 1 over x, all right, we could see that as x approaches infinity, y gets closer and closer to 0. That's pretty much what it means. Now you could evaluate it by substituting in infinity for x. So like plugging that in right there. Now if we think about it, does that equal 0? Well, we're going to say it does. All right, if you were to take $1, and just divide it an infinite amount of times, you're eventually going to have nothing left. Anything. If you just keep cutting it up into more and more pieces, dividing it into more and more pieces, you're going to end up with nothing if you do that infinitely. All right, so this right here, 1 over infinity, or really any constant over infinity, is going to equal 0, is an important idea to understand this next topic. Okay, so we're going to do a little investigation here. I'm going to demonstrate it. So we have n and d. So if we had a rational function, it's not writing, f of x is equal to n over d, where they're both functions. N is the degree of the numerator, d is the degree of the denominator. So we're going to look at what happens when the denominator has a bigger degree, what happens when they have the same degree, and what happens when the numerator has a bigger degree. Okay, here's an example of a function where the denominator has a bigger degree. It's a linear divided by a quadratic. Notice how it's a horizontal asymptote at the x-axis, y equals 0. Alright, well let's say I make this quadratic and make this a cubic. Alright, still has a horizontal asymptote at 0. Alright, let's say I make this 100. Alright, looks kind of weird. Doesn't really have a horizontal asymptote. But as you zoom out, it will have a horizontal asymptote that equals 0. Alright, so any function, rational function, where the denominator has a bigger degree is going to have a horizontal asymptote at y equals 0. Alright, so that was just a demonstration of looking at different examples. But now I'm going to try to prove it to you. Okay, so I'm using y equals x minus 4 over x squared minus x minus 12. Alright, first thing I'm going to do is divide all these terms by x squared. Okay, kind of sloppy, but I took all those 5 terms and I divided them by x squared. Okay, now I'm going to simplify it. Okay, so that's what we have now. Okay, now I'm going to see what happens when x gets really large. So to kind of symbolize that or illustrate that, I'm going to replace all my x's with infinity. Okay, now if we look, 1 over infinity is going to be 0. Okay, if you take 1 and divide it an infinite amount of times, it's going to be 0. If you take 4, all right, infinity times infinity, still infinity. You take 4 divided by that, still going to be 0. Okay, 1 minus 1 over infinity, all right, that's going to be 0. And then 12 over infinity squared, that's going to be 0. All this here simplifies to 0 over 1. So by plugging in infinity, we're seeing what happens as x approaches infinity, and we see that y is going to approach 0. All right, so that's a proof of why horizontal asymptotes are going to be the x-axis for rational functions where the denominator has a bigger degree. Okay, now let's look at a rational function where the degrees are the same. So a quadratic over a quadratic. All right, this is going to have a horizontal asymptote at y equals 1. So let's do that same experiment, divide everything now by x squared, and see why that happens. Okay, so here is the step where I divide everything by x squared. All right, now I'm going to simplify it. Okay, and that's what that looks like. Now to demonstrate kind of algebraically why the horizontal asymptote is at 1 when x gets really large, I'm going to plug in infinity for x. All right. In other words, I'm seeing what happens to f of x as x approaches infinity. Now this part right here is going to equal 0, this part will equal 0, this part will equal 0. So it simplifies to 1 over 1. Hence why when x gets really large, y is going to get closer and closer to infinity. Now let's say I kept it as a quadratic over a quadratic, but I changed this leading coefficient to 2. Alright, well then that would change this to 2 and change that number to 2. Alright, so think about how's that going to change the graph and the horizontal asymptote if I did that. Alright, and you could pause it and then in a second I'll show you the answer. Okay, so I'm going to take the 2, Alright, plug that in right there. Oh, sorry, should have gotten that ahead of time. Alright, and it looks like it moves up 1. Alright, and it does. We have a horizontal asymptote at 2, because if you simplified that previous thing I just erased, it would simplify to 2 over 1. Alright, so now, and I'm running out of time here, but in the next video, we're going to look at what happens when the degree of the numerator is higher.